Now his first article, that was on the 17th of March, so 145 years ago almost, and not 145, sorry, 119 years ago, and this is the German title. Of course, he wrote in German. He spoke German. You later learned, of course, you learned English, but Germany was at that time one of the most important countries, especially in physics, right? So before that, it was definitely England with all their scientists. Later on, of course, it's the United States, but at that time it was Germany. So writing in German for a scientific article was pretty normal, basically. I've translated the title, and then still it's quite heavy to understand. But the original German, I can't read German really well, so I have a pretty good translation in Dutch, which I could read. But the original German is very formal, and that was the way of writing scientific articles at that time in Germany. So if you translate it, it's still pretty formal, but that's the way they wrote. And as you can see, it gave an explanation for the photoelectric effect. So classical idea was about the photoelectric effect is that you shine light on a substance and out come electrons. And basically they thought, well, light is energy, and if you put energy into matter, then electrons come free. But the classical idea is that the electrons gather enough energy, and at the moment that they have enough energy, then they are emitted. And basically Einstein said, no, that's not the case. It doesn't help if you shine a lot of, let's say, red light on mass. A lot of red light has a lot of energy, but the electrons can't gather all the energy. You have to shine light with the right frequency, so the right energy on it, and then even one photon is enough. So basically, for low energies, low frequencies, nothing happens, but if you reach the right frequency, then the electrons are emitted. Only at that, so you don't need a lot of red light, you only need a little of, say, blue light or ultraviolet light, and then they are emitted. And he also said that light consists of, well, packages, energy packages, and not waves. So very different from the classical idea. So the thing is that energy comes in packages was not his original idea. It was thought of by Max Planck when they were trying to solve a physics problem that they had, when they were describing black body radiation, heat radiation, for stars, for instance. So objects with low temperature they could describe very well, but basically at higher energies and higher temperatures, it's called the ultraviolet catastrophe. Basically the model fails, it goes to infinity, so it doesn't work. And Max Planck basically found this mathematical trick to solve that problem, that it doesn't go to infinity but it goes to zero again. And he introduced that the energy came in packages. He didn't really believe that energy actually was distributed in packages, but it worked in the model. Einstein said, well, the thing is, they are. The light is exactly in packages, in small packages. And basically it was the start of quantum mechanics. Quantum mechanics is about things in nature being distributed in finite bits of energy or mass or charge or whatever. And that this finite smallest bit you can't divide any further. So the same thing for energy, and perhaps you can find it already where he mentioned it, but it's here. He called it energy quantum. So the smallest amount of energy that you can't divide any further. Like the electron charge, that's the smallest charge that you can have. You can't have half a charge of that. Well, with energy, the same thing. So this was the start of quantum mechanics, basically. So while he was at the start of quantum mechanics, later on he had a lot of trouble with the implications of quantum mechanics, because quantum mechanics is really very strange and has a very strange applications and everything. So it's really hard to grasp, and he had trouble with that till the end of his life. Some of the consequences we probably know. This thing that light can be seen as waves, and the wave model works perfectly in some cases, but also as a particle is called the wave-particle duality, so that a thing can be two things. And later it turned out that electrons have this duality also. electrons were seen as particles before, but then they found that you can also treat them as waves, electrons as waves, and that also works. So that is very strange. That things that you thought, well, they are waves, like water. Water wave is a wave, and like sound waves are waves, and light is a wave. That can be a particle, and that a particle can be something like a wave in a sort of infinite wave. That's very strange. Well, Niels Bohr used this light quanta model to base his atomic model on, and that's a very familiar model. You knew that it's not exactly this, but it worked, right? And these energy quanta, light quanta, were later called photons. So that was a name that was invented later. So a photon really sounds like a particle, like an electron, a proton, a photon, and that was only later. So Einstein himself called it energy quanta. And of course, we have some applications. Lasers were, oh, wow. So where is it? There it is. So lasers are based on the idea that energy is in packages. And now the newest thing, or one of the newest things, is photonics. So instead of electronics, where we use electrons to connect stuff, we also can use basically light particles. And photonics is the next thing in the development of all kinds of applications.